etc. Right? a long title. Right. Well, I will not give a general theory. I will consider simple examples, and were quite useful, which actually related to study by in 2 centuries maybe ago in the Hilbert School, and later on Weierstrass, Frobenius. That was popular. But what we discovered that there is some natural link to finite dimensional integrable systems, which we want to draw your attention. Basically, summarizing what Victor said in his lecture, in his talk, the motivation of our study, in a sense, to give a nice, well-defined set of Lie algebras which are infinitely dimensional. In infinitely dimensional case, it's difficult to, for infinite dimensional algebra, it's difficult to solve the problem of isomorphism because you have infinitely many relations to check. But if it has a structure of finitely generated module over some Noetherian ring, then only a finite number of structure elements have to be checked, and if that is a finite problem, so that is why we go in this direction. And but I don't want to go to very general, and I will consider a very concrete example of such algebra, and we'll see what we can do with that. And as example, we will study, first we will study a symmetric square of hyperelliptic curves. I describe it as a manifold or in terms of coordinate ring. Then we discuss the vector fields or algebra of derivations of the corresponding ring. Then we touch one problem which had been solved by Arnold in his book and by School of Arnold, and we find very nice short solution of the problem, quite interesting, that I would like to share with you. And usually if you look on the symmetric square as a bundle, then there is a problem of lifting of vector fields from the base, and we will see that if we have Witt algebra structure, then this lifting is unique. We will show this lifting, and the vertical derivations will commute, and will as you have derivations of vector fields, they obviously link to dynamical systems, and these dynamical systems will be integrable, Hamiltonian. That's what the plan. Right, first let's discuss what is a symmetric square quickly. Symmetric square is a very can be seen in the following. Well, there are many ways to describe it, but it's a very constructive and simple way. So let's take C2 with coordinates x, y, and then we have a polynomial y square minus some polynomial of degree n with some roots, and the manifold of corresponding, so the corresponding affine varieties is a hyperelliptic curve, and the genus of this curve is n-1 divided by 2, the integer part, if the roots not coincide, if the curve is non-singular. That is one curve. Now we want to consider symmetric squares. To go to symmetric squares, we consider two copies of the same curve. Same curve, that means has the same branching points, where the two copies. So we have Cn plus 4 n roots and 4 C2 and C2. And so we can consider first the affine variety, which it's a common roots of these two, that this two curve. And on this variety, there is natural action of the group S2 and Sn. Sn, which permute the roots, and S2, which it's an involution which swap x1, y1 to x2, y2. And the symmetric square in geometrical terms is a series of orbits of our manifold over this group. But that is kind of in this language. Let's go to more constructive language, namely let's consider the in terms of rings. So what we do, we can consider the ring of our polynomials with n plus 4 variables and the ideal generated by two polynomials which defined our curves. So the coordinate ring of Rw of our manifold W is, of course, the quotient ring here, and to go to the coordinate ring of the symmetric square, we need to take the average and consider, the average, the invariant subring of this ring with respect to action of our group. Here notations EI standard symmetric polynomials, I will use it. And indeed, if you use our polynomial, it's automatically invariant with respect to permutation of the roots, because if you open the brackets, the coefficients are symmetric polynomials. So nothing to take average over Sn in a sense, but S2 require some work. So the classical problem which been tackled by I think in Hilbert and in the book of Gelfand, Kapranov, Zelevinsky, how to construct what is the symmetric power of C2. So what we have? We have C2 by C2, so we have 4 coordinates, and we have our involution. So the first proposition is that, of course, this ring of invariant can be written in the following way. So we consider a ring of 5 variables and an ideal generated by the syzygy. This syzygy. Usually, if people use a standard system of coordinates, standard basis of invariance, this syzygy is 2 lines or very long. But we managed to find a very nice set of coordinates which are written here, and obviously they are all invariant. And in this case, syzygy is a very simple, and that's what is a manifold. Basically, what we can say that the symmetric square of C2 can be embedded on C5. Actually, it's the zeros of this polynomial. That is the answer. Now, all our structures are graded. We can make everything homogeneous if we assign weights or degrees of weights to x, and x is 2, y is n, is a power of polynomial, and the roots also have this power, and we have some strange notations, look, n plus 2n, etc. These notations just reflect the degree of the weight in the grading. So looking on any expression, you just take the sum of these degrees, and you know the weight of homogeneous elements. So now we can say what is a symmetric square in this language. The symmetric square is the following. We consider the ring of n plus 5 variables. So there are 5 variables here, and y correspond to branching points, and the coordinate ring is a quotient over the ideal, and ideal generated by these 4 polynomials. And actually, in some ordering, these polynomials form a Gröbner basis of the ideal. So it's easy to compute things then. So one is, of course, the syzygy we were talking about, and another comes from the curve. Everything is explicit. Everything is given in a finite. So if you fix n that are polynomials, you can compute every coefficient. So that is a complete description of the coordinate ring of symmetric square of hyperelliptic curves. And of course, the symmetric square of hyperelliptic curve is a variety corresponding to this ideal. Now, what we notice a quite interesting thing. I don't know that here, if you allow to divide by U4, if you look at this, so here is polynomial ring. But if you allow to divide by U4 by one letter, then you can solve all the polynomials, all the elements in the all these equations, and describe this manifold as a rational manifold, because you will have only U4 in the denominator and nothing else. and you can solve, and that immediately motivate a homomorphism of Cn plus 2 to Cn plus 4, or homomorphism of the rings in opposite direction. So, and that is exactly what happens. We can introduce n plus 2 dimensional space, and in this n plus 2 we have explicit form of transformation, this morphism and that this fact was known. Usually people say that there exists a birational isomorphism of symmetric square of hyperelliptic curves and Cn plus 2. But here is explicit form of this homomorphism. Moreover, we even see what kind of submanifolds we have to remove to make it one-to-one. So that is explicit thing. Now let's go to, I don't control time. Let's go to definition. Now we go to vector fields and to algebra of vector fields tangent to our manifold is obviously derivations of this quotient ring. So derivation that is the same thing, just in the language of the quotient ring, and we need to define two, because this structure has a natural bundle structure where the base is the base is a space of base is the space of where branch points or parameter of the curves, and x and y big is on vertical in the fiber. So therefore, in our ring we have two groups of variables. One would correspond to the base a1, an, and b is a vertical, and we have ideal. That is kind of general derivation, probably well known. So we say that a derivation of quotient ring, of course, should respect the ideal, so should send ideal into itself, and we call derivation to be vertical if it acts on the first group of variables. The result is in the ideal, that is vertical derivations, and horizontal derivations, or projectable derivations, are derivations on the base which can be lifted to the coordinates b to the whole bundle, and that is a precise definition. Basically, in coordinates, if you don't want to look on precise definition, means that derivations of vertical derivations are derivation along the fiber, and horizontal derivations are derivations along the base, but they are not derivations of the, they don't respect the ideal. In order to make it a derivation of the quotient ring, we need to respect the ideal, and therefore we have to correct this derivation of the base by extra terms. So that is projectable. So if you act only on a base, it's a derivation on a base. You can project it. Of course, there are other derivations which not of that type. Right. Now we move to a classical problem being solved by Arnold in 60s, in 70s, 80s, and his school, Fuchs, Zakalukhin, Giventali, lots of people contribute. And the problem was the following, that let's consider Cn with the condition, so hyperplane in Cn. And in this hyperplane, and also we consider the discriminant set, so the planes where xi equal to xj. Now Arnold set a problem to describe vector fields which is tangent to the discriminant set. That is one thing, and they show that also respect this condition, and the Zakalukhin shows that there is a basis in which these vector fields have a symmetric matrix if you act in the basis of elementary polynomials. And Ilvik later formulate a conjecture that acting on the discriminant, this vector field will give you discriminant with such a very simple eigenvalue, I would call. In the terms of rings, that can be formulated in the following way. We consider the polynomial ring of n variables, Cn. Now, we need to find such derivations of this polynomial ring which send symmetric polynomials into symmetric, which send the respect the ideal generated by the discriminant polynomial, which has a symmetric matrix in the basis of elementary polynomials, and respect the ideal generated by the sum. So that is the problem formulated in terms of rings. If we forget about the spaces and the original geometrical construction. And we will show a very quick and short solution of this problem, very nice one, which we will use later for our symmetric squares. First, we need to introduce Newton polynomials. We have a standard basis of standard symmetric polynomials, and that is the Newton polynomials. Newton polynomials is a sum of case powers of I, obviously symmetric, and there are infinitely many Newton polynomials. Of course, only finite number, or first n, are independent, and higher Newton polynomials are polynomial of the lower. And the ring of invariants with respect to permutation is isomorphic to this. They are all isomorphic, of course. Now we define so-called, so we call it Newton derivations. I don't know if they are really being used in literature, but they prove to be very, very useful in our problem. Newton derivations are the following. You have dx that are derivations of Cn, obviously. They have a very simple and clear form. These Newton derivations almost solve the Arnold's problem, and we will see how we can, starting from Newton polynomials, solve the Arnold problem. First of all, Newton polynomials obviously send symmetric polynomials into symmetric. Indeed, it's sufficient to look how they act on Newton polynomials, Newton derivations. They form a faithful representation of the Witt algebra W minus 1, which Victor told in his talk. So if you commute these two vector derivations, you will get obviously this relation, and that is n-dimensional representation. And it's very easy, maybe 2 lines or 3 lines, to check that if you act on the discriminant polynomial, you will have discriminant polynomial, and the coefficient will be a symmetric polynomial. So that is easy to do. So what I summarize, it's a derivation of Cn. They send symmetric to symmetric, and they respect the ideal generated by the discriminant polynomial. Actually, from our Witt algebra, immediately follow this nice identity for Newton polynomials, which seems to be new. We ask specialists, and that is very difficult to find something new in symmetric polynomials, but it seems it is. So that is a new. Of course, only n derivations are independent, and all other can be expressed explicitly in the basis of n, and these coefficients we know can be easily written. There is a generating function for this coefficient. These derivations are derivations in the base, where we have xi, if we consider x1, xn are branch points of our curve, they act on the base of our bundle. And they don't respect the ideal generated by our curves, by pair of the curves. We can, before, sorry, I'm a little bit too fast. I'm a bit too fast. These Newton generations, derivations, it's useful to introduce generating function or generating vector field. So if you take the sum, you can have obviously this expression. So everything can be expressed in terms of generating vector field. And how to make the matrix symmetric in elementary symmetric polynomials. Let's act by generating vector field to generating function of elementary polynomials. That is generating function of elementary symmetric polynomials. If you act, it's a very short computation show you this one. And you see, you can make it symmetric with respect to t and tau, just multiplying by t et. It's just a function. If you multiply, then this thing will be symmetric with respect t and tau. And if you expand, that means your matrix will be symmetric with respect to in this basis. So that is almost a generating function for Arnold polynomials, Arnold derivations. This L is a derivation of the ring sent ideal into ideal and has a symmetric matrix. What is missed? The property that the ideal generated by the sum is not respected. But that can be easily corrected. And this function is a generating function for Arnold polynomials. So Arnold vector fields now can be found just taking expansion of this generating function, which is a polynomial in T actually. That is exactly will be Arnold derivations. Well, I will not stop on Ilbig, the proof of the Ilbig conjecture, because no, I have to respect time. Yes. Now we come back to symmetric square. I remind you that we have a structure, that we have a base. It's a space of parameters of the curve or branch points. This is a space, and we have a fiber which is a symmetric square with the fixed values of branch points. And if you look on our Newton derivations, which acts on the base, we will make now projectable vector fields from that. That is projection to the base. They act on the parameters, on the branch points of our bundle. But these derivations don't respect the ideal generated by the curves. They don't know anything about the hyperelliptic curves, which grow above the fiber, above the base, above the fiber. But that can be corrected. And they correct it by adding this, well, here this theorem not about the square, but m's power. If you take m equal 2, it will be square. So you can correct that by adding this little term, and you can check that, well, this term was found just by solving the equation that they respect the ideal, and we know that Newton derivations satisfy with algebra. So we request that the lifted derivations, which acts on the whole bundle, on the whole symmetric space, also give us representation of with algebra, and that makes lifting unique. Because usually we can, when you lift, you can add all these vertical derivations, which does not spoil anything, and it's a not unique way to construct derivation or vector fields, projectable vector fields of the bundle. And that property of with algebra makes it unique, and that is an explicit formula for a generating function of projectable derivations. And that relates to the problem in if n equals 3, it's related to the problem solved by Weierstrass and Frobenius when they study how you can differentiate elliptic functions with respect to parameters g2, g3. If you differentiate, you lose ellipticity, so you have to correct the vector field in order to map elliptic function into elliptic. And that is a way that formula solves this problem for hyperelliptic, for symmetric squares, symmetric powers of hyperelliptic, including elliptic as well. Now let's talk about vertical derivations. That means we have a fixed branch points, so branch points is fixed, and we have a couple of we have a symmetric square of a curve with fixed points. First, a very general lemma. If you have a plane curve, smooth, I mean, twice differentiable is sufficient, but well, in all our case, we have polynomials, so they're as many as we wish differentiable. Let's a curve function. We have f function f of xy twice differential. Now we define decay, and decay is a vector field, or is a derivation which we can apply to this function. And we define decay and define two vector fields. Here there are some denominators which I will discuss later, x1 minus x2, so that are two vector fields in the space of smooth function of x, y, everything. Now, it is easy to check that these two derivations commute. So if you commute for any f, they will commute. And they map symmetric with respect to this involution function into symmetric. So they respect symmetric square. That is two derivatives. That is a general lemma not related to just for any smooth curve. If we're going back to our hyperelliptic curve, and also let us assume that the roots of the polynomials not coincide, so the curve is non-singular, then actually any derivation of this curve of that form dx dy is proportional to this derivation. So this choice of function is not actually arbitrary, it's unique. You can try to show that that is unique. Now, doing so, now I want to apply these ideas to our symmetric square. But in symmetric squares, we have always worked with polynomials, and we did not. And here we have some denominators, and you may say that okay, we get out of polynomial ring. So there is a very surprising observation that if we use our homomorphism that I described before, from Cn plus 2 to Cn plus 5, and that induce the isomorphism of the ring, then in new variables, these derivations are polynomial. They always polynomial. So if we divide, we can divide only by u4, and u4 is x1 minus x2 square. So if you just divide by u4, you can show that all the derivations are polynomial. Here, the example for n equal 5. And this is, and we know that if they are polynomial, they correspond to polynomial systems because they commute. That means one is symmetry of another. Then we will see they have enough first integrals, and they have direct relation to the theory of integrable system. For instance, for finite gap integration, if you denote L1 as a dx and L3 as dt, then you can easily check, and u is 8 u2. I just put, this scaling in order to have, some coefficients which we can recognize. Then you will get Korteweg-de Vries equation and its symmetry, and that corresponds to gap solutions of the Korteweg-de Vries equations in hyperelliptic functions. So that is a known stuff, but that is a case when the genus equal to and the power equal and symmetric power equal to. But what we consider when genus now is, if genus and symmetric power coincide, then the symmetric power of power g of hyperelliptic curve of g power of symmetric or g symmetric power of hyperelliptic curve of genus g is birational isomorphic to the Jacobian of the curve. But we consider the case when the symmetric power, we have symmetric square in this, we have in plans and some results for arbitrary power, but in this particular talk, I'm talking about symmetric square of hyperelliptic curve, and the genus can be any. For instance, genus can be equal 1, elliptic case, 2, then that is Jacobian, 3, when etc. Let's look what happens, what the systems will. We can find out using this idea, using these commuting vector fields. One observation, recent observation actually, which some of the result of this paper been already published, but that is rather recent observation. Actually, the dynamical system or vector fields which we find are Hamiltonian. So there is a natural Hamiltonian structure, and that is a non-zero Poisson brackets, which we have. There are the Poisson brackets of all variables. So we have 4 variables in 4-dimensional space, real. So we have variables u4, u2, vn minus 2. The index correspond to the weight in the grading. And there are only 2 non-zero Poisson brackets. So if you have this, then all systems, all vector fields are Hamiltonian, and we can look at on these vector fields. Let's consider simplest example, n equals 3, when the curve is elliptic. That is elliptic curve in our annotations. We L1, L minus. We have these two commuting vertical vector fields. We define, in order to have more readable notation, we say that L minus 1 is d psi and L1 is d eta. Sta means vertical. And then the corresponding vector fields yield these two commuting. So we consider vertical vector field on a symmetric square of elliptic curve. This elliptic curve is considered symmetric square of elliptic curve. That is, by Macdonald's theorem, is can be seen as a fiber bundle with a base elliptic curve, and the fiber is a CP1. And if you look on the system, you see the manifestation of that. So that is one equation. That is another system. That correspond to L minus 1, and that correspond to L1. Moreover, this system has two integrals, and integrals, of course, the constants y4 and y6 are branch points. We have vertical derivations. They don't touch the branch points, so they are first integrals. And these first integrals are nothing but Hamiltonians for this system with respect to this Poisson bracket. If you look at this system, you can ask yourself, can we solve this system? And the answer, yes, we can solve this system, and that is a general solution. General solution, yeah, I know I have a few minutes, 2 minutes. So general solution is here. So it's polynomial in psi and elliptic, actually not elliptic, but zeta function, Weierstrass function in eta, and that are four parameters. Because it's a fourth order equation. And the last equation is for n equals 7, because n equals 5 give us abelian function, and that is known result. That is a new result. N equals 7 give us a symmetric square of the curve of genus 3. That is a corresponding system. The claim is that that is a first integrals. The system is Hamiltonian. That are Hamiltonian of this system. We have everything we can, and that system can be integrated, and actually been integrated recently by Buchstaber and Ayana, and they show that cannot be integrated in a abelian function, but can be integrated in a meromorphic function of so-called sigma divisor. I don't have time to discuss these things. And that's it. I will not repeat what I said. No questions. Oh. Yes, it's not. It's the question was that I pointed on two classes of derivations: vertical derivations and projectable derivations, and I mentioned that that's not the all derivations of this ring. So there are other derivations which are not vertical and not projectable. Basically, yes, there are, and having these derivations, vertical and projectable, you cannot construct all. They don't form any basis, but they have, and they, I would say, naturally associated with the fiber, with the bundle structure of the manifold. But there are, derivations which are not in this class. So we know these derivations, we can compute these derivations, but we don't see any use of this derivation up to now. Yes. Poisson brackets. So we have oh, sorry, too far. We have 4 variables. In C4, we have actually R4, because in this case, if your parameters y are real, then everything real, and then it makes sense to talk about R4. So the reduction to real case is a very kind of obvious. And in R4, we have 4 variables, v n minus 2. N minus 2 reflects the weight. And u4, vn, u2. And basically, you can say that u4 divided by 4 are canonical coordinate, and vn minus 2 is the corresponding canonical momenta. And u2 divided by 2 is canonical coordinate, and vn is a canonical momenta. That is a canonically conjugated, the canonical structure where the Poisson bracket has a standard form. And now, if you just use our first integrals, which can be easily found using the homomorphism that I said, you know, this, I said that we have some homomorphism of Cn plus 2, that we have some map of Cn plus 2 to Cn plus 5, and which correspond to the homomorphism of the ring. Then we have we can express 2 last coefficients in the curve in terms of our letters. We can resolve this system, and they are Hamiltonian for this system. So that is so you can even ignore everything. You just can start from the curve, compute these 2 coefficients. They are Hamiltonian after this map, and compute. So we find a class of integrable polynomial system in C4, which are Hamiltonian. In R4, yeah, we can do it, I believe, in R2n. In the same manner, if you consider n as in R2k, where k is a symmetric power k. So that will yield in R2k. Integrable systems, commuting flows, first integrals, everything classic by Louville, Lee, everything classic here.